and we'll move on from there, and then we'd probably do the same on the other side.
Right. So basically, on the left we have a matrix multiplication. On the right we have a scalar multiplication and a addition, just projection. So basically, let's do all the operations that are implied here. So if I multiply the two matrices on the left, what I get is xy plus 2x times y plus 2. So that right there is all the top left entry. And then top right is going to be row 1 by column 2. So 3x plus x times y plus 2. Then y times 5 minus y plus 2x. And then 3 times 5 minus y plus x. So I think that's, by the way, double check. If you think I did something wrong, it's very possible. It's a lot of things to keep track of there. The right-hand side, I'm thinking is going to be a little simpler. So because I'm doing, I think I can do the scalar multiplication and the subtraction all at once. So if I want the top left entry, it'll be 2 times 1 minus y. So 2 minus y. Then 2 times 0 minus 1, so negative 1. 2 times 0 minus x, so negative x. And then 2 times x minus 0, so 2x. So I think now that we've set it up like this, we have a 2 by 2 equals a 2 by 2. So in order for us to have equality between matrices, what do we need? Like, what do we need to set up? Like, what are our conditions?
We have to set the entries on the left equal to the entries on the right and try to solve for one variable, I guess.
Right. So how many equations am I going to have to solve?
Looks like maybe 4.
Yeah, exactly. So I'm just going to write one of them out because the rest are going to follow suit. So one of the 4 equations I have to solve is this: xy plus 2x times y plus 2 is equal to 2 minus y. And that comes from equating this entry with this one. So I think the question you asked, James, like we can stop here, right? All we had to do was set up the equations. Okay. So yeah, solving this would be, yeah, take a lot more time. But the idea here is about, at the heart of this question, what does it mean for matrices to be equal to one another? And all their corresponding entries have to agree. And what's kind of implied in that is they have to have the same order, which these do. We have a 2 by 2 matrix being compared to a different 2 by 2 matrix. So here's equation 1. The other 3 are going to come from the other pairs of entries. Right. Does that make sense, James?
Yes. Thank you.
All right. No problem. Sounds good. All right. Who's next?
I have another one.
All right. Let me give everyone. Does anybody else have a question before I? Otherwise, I'll let James go again. Oh, I got something in the chat. Yeah. So somebody's asking me if there's a key to the sample final exam. I don't have one. So what I can do is, as soon as I get off this call, I can send out the answers. Like I can figure out what the answers are and send them out. In the meantime, if you want to go over anything from that sample final, let's do that. I think that'd be I think that'd be a valuable thing to do.
That was just the rest of my questions. So
Oh, really? The sample final?
yeah.
Okay. I mean, we might have, so I have at least two people asking about that. And it sounds like Quinn is seconding it. So yeah, let's go ahead and do that. So I don't have that up. Can I get to it without screwing up my whiteboard? No, I think I can. All right. All right, sample final exam. Okay, so the first question is the one you asked me already, James. Second question. I mean, I have no qualms about going through this whole thing if people think that would be value added for them. So the second question is basically given a set of three vectors, can we use Gram-Schmidt to replace those three vectors with an orthonormal basis? So I'm kind of just looking at this thing in order. If that is something we can, is that something we should do next, the Gram-Schmidt process? All right. I'm just going to go ahead and start there unless anybody has strong feelings. Monica's asking what sample final this is. So I posted two files. One of them was a single test, and the other one was like 24 pages long. The one that I'm consulting right now, this is just the single one. So it's called MAT 242 sample final. And this is question 2 from that file. Okay, so here is the objective. I have these three vectors. They're a basis for something. What I want to do is replace this set of vectors with another set of vectors that's orthonormal. So what does it mean? What is an orthonormal basis? Or how do I start doing this? So someone's saying this is not on the website. I don't know if this is on the MA2 so I don't know if this final is on the MAT 242 website. I posted this to Canvas. So it might not be on the math.asu.edu, that website. It is definitely on the week 6 module on our Canvas under the exam prep heading. So I want to take these three vectors and convert them to an orthonormal basis. How do I go about doing that?
You can if I'm not mistaken, the first vector, the like I know how you're supposed to separate them from old to new and then
Yeah.
new 1, 2, and 3. I think old 1 is just equal to new 1. So you just automatically get that one.
Right. So I'm just gonna go left to right. So I mean, basically the game here is I want to replace these three vectors by a set of another set of three vectors that are orthonormal to each other. So I'll let you all tell me what that means, what orthonormal, like what's required for that to happen. But basically, my concern is that these three vectors have some kind of conflict with each other. Any one of these vectors is fine. I can use any one of them as a starting place. So what I'll do is this: I'll say u1 is equal to 0, 1, -1. So now the obstacle becomes, what do I do? How do I generate u2? How do I build another vector that doesn't create those conflicts that I'm worried about? So if that's u1, then what is u2? More importantly, how do I build it?
On the at least one of the three that large file of practice exams that has you do new2 or like vector2 is the old like second old vector subtracted by a fraction of old 2 times new 1 over new 1 times new 1,
Okay.
and that fraction multiplied by new 1, I think.
All right. So basically what's going on here, so I agree with the calculation you set out. Here's why that works. So here's the u1 that I started with. And basically what I want to do is break down v2, or what you're calling old 2, into two pieces. u1 and v2 are not perpendicular to each other, but I can break v2 into two different pieces, one of which is fully parallel to u1, and one of which is fully perpendicular to u1. I want this one, the one that I'm putting a question mark on. That's the one I want. But in order to find that, I need to figure out what the parallel piece is, which is what, this set of dot products is for. So u1 dot v2 over u1 dot u1 multiplied by u1. So this thing right here, this like ratio of dot products, what that's basically going to tell me is what portion of u1, or sorry, what portion of v2 is in the direction of u1. All right, so let's find this dot product. Let's actually go ahead and fill in all these details. So v2 that comes from the original set. So that's the second vector from the set that I gave you. And then what is u1 dot v2? So it should be 0 times -1 plus 1 times 0 plus -1 times 1. That's -1 over u1 dot u1. So 0 plus 1 plus 1. So 1/2 of u1. So 0, 1, -1. So if I complete this, what should I get? -1 plus 0, -1. 0 plus 1/2 of 1, so 1/2. And then 1 plus 1/2 of -1, so 1/2 again. So I believe this right here is u2, or the way Quinn worded it, new 2. So we're trying to find new 1, new 2, and new 3. So we got 2 of them. One of them we just took as is. The second one we had to manipulate a little bit. But now we should be equipped to find what U3 is.
Could you go back through how to do the dot product for the U1 V2?
Yeah, so I'll do U1.V2 since those are different vectors. So U1.V2, what are the details there? U1 is 0, 1, -1. And then V2 is -1, 0, 1. So the way you do a dot product is to take the corresponding pairs of components, multiply them. That'll give you 3 different products. And then you take the sum of all those products. So 0 times -1 plus 1 times 0 plus -1 times 1. So and if you write the vectors down in their column format like this, you're looking straight across. So the only one of those that is not 0 is -1 times 1. So that's why I get a dot product of -1. And then you can do, same process for U1.U1, except you're multiplying the components of the vector by, you're squaring all of them and adding them together. So again, that is how to do a dot product. That ratio basically tells us informally speaking, how much do V2 and U1 have in common? How much, how similar are their directions? All right, so now I have U1 and U2. Now I want to build U3. So the way we build U3 is, well, it's going to be based on V3. But what I want to do with V3 is this. I want to remove from it all of its, basically all the directionality that it shares with the other vectors. So if we back up to U2, U2 was based on V2, but we wanted to remove the directionality that it shared with U1. So I'm going to have to do that again. So I'm going to dot U1 with V3 and basically find that this thing we call the orthogonal projection. Or in my diagram here, what's the parallel piece? If I were to break down V3 into 2 parts, what's parallel to U1 and what's perpendicular to U1, I want to remove that parallel piece. But there's a second vector I got to avoid as well. So I'm going to dot U2 with V3. So basically, the more vectors you want to make, the more, basically, we build them one at a time. So with each new vector, you have to avoid sharing any kind of direction with the previous vectors. So to build U3, here's our template. Now we got to fill in the details. So what is V3? That is 1, -1, 1. U1.V3. So that dot product will be 0 times 1. Can you all see my pencil cursor?
Yes.
Okay, good. So this dot product will be 0 times 1 plus 1 times -1 plus -1 times 1. So -2 over U1.U1, which we did a while ago, and that was 1. Or no, it was 2. I'm sorry, it was 2. So -2 over 2. So that's the ratio I want, multiplied by U1, which is 0, 1, -1. And then we got to subtract off the piece that basically the agreement between V3 and U2. So whatever directionality they share. So U2.V3, U2 is negative, so -1 times 1. So -1. 1/2 times -1. So -1/2. And then 1/2 times 1. So +1/2. All over U2.U2. So U2.U2 is going to be 1 plus 1/4 plus 1/4. So that's going to give me my ratio, all of that multiplied by I didn't write this down. U2. U2 is -1 times 1/2 times 1/2. So let's clean this up a little bit. So this will be 1, -1, 1. This ratio just came out to be +1. So plus 0, 1, -1 minus, what did this come out to be? These cancel. So I get -1 over 1 plus 1/2, so 3/2 times -1, 1/2, 1/2. Looks like I'm adding again. So what is 1 over 3/2? That's 2/3. So let's do some more simplifying. 1 plus 0 is 1. -1 plus 1 is 0. 1 plus -1 is 0. So 1, 0, 0 plus 2/3 times -1, 1/2, 1/2. So 1 minus 2/3 will be 1/3. 0 plus 2/3. So what's 1/2 of 2/3? That's 1/3. So 1/3, 1/3, 1/3. So I think that is U3. So how do we know if we did this right? So we have U1, U2, and U3. That was the goal. How do we know if we did this correctly? What should we check?
Do we check that all of them like multiply together gets us the zero vector, right?
Very close. Not the zero vector, just 0, because what's the way you're going to multiply these things together, these three vectors? What specific product are you trying to get?
Like a linear combination.
Oh, not quite. So I have U1, U2, and U3. So I replaced the V1, V2, V3, that basis with this new basis. Well, partly. The first one I just kept as is. So 0, 1, -1. Then my new vector 2 is -1, 1/2, 1/2. My new third vector is 1/3, 1/3, 1/3. But this new basis needs to fulfill some requirements. What requirements are those? We have this word orthonormal, but we haven't really unpacked what that meant. So what does it mean for a basis to be orthonormal? So basically there are two things we have to watch out for. One is that we have to have vectors that are all orthogonal, and they all have to be normal. So what does it mean for a vector to be normal? A vector is normal if its magnitude is 1, if its length is 1. A set of vectors is orthogonal if all of their like dot products, like you take them 2 at a time, if all those available dot products are 0. So I think one of those is true right now. If you were to dot any 2 of these vectors together, I believe you would get 0, which means that pairwise, they're all orthogonal to each other. They're all perpendicular to each other. We can do those if you want, but I'll let you verify that those dot products are all going to be 0. So that one I'll check off. What we don't have right now is normality. None of these vectors right now have a length of 1. So how do I do that? How do I adjust these vectors so that their magnitude is what I need their magnitude to be? Let's start with this. How can I find their magnitudes? How do I find the magnitude of 0, 1, -1?
It's the you find basically it's the Pythagorean theorem.
Yeah, so Pythagorean theorem will give us the magnitude. So let's go ahead and do that. What's the magnitude of 0, 1, -1? That'll be 1 squared plus 1 squared, 2. So the magnitude is the square root of 2. So because of that, if I want to normalize this first vector, I can just multiply the whole thing by this scalar, 1 over radical 2. Doing that will give the overall vector a magnitude of 1. What's the magnitude of this next vector? So -1 squared plus 1/2 squared plus 1/2 squared. So 1 plus a fourth plus a fourth. That's 3 over 2. So then what is the magnitude of that vector? Well, it's the square root of 3 over 2. So I can divide by that, and that'll basically give me the square root of 2/3. And then finally, what's the magnitude of 1/3, 1/3, 1/3? So 1/3 squared plus 1/3 squared plus 1/3 squared is equal to 1/9 plus 1/9 plus 1/9. 3 over 9 is the same as 1/3. So what can I divide that last vector by? I'm going to divide, or basically multiply it by 1 over the square root of 3. So before multiplying by all those scalars, I had an orthogonal basis, but I didn't have an orthonormal basis because all the lengths were, or at least one of the lengths was different from 1. Now they're all equal to 1. So this is a good Gram-Schmidt approach to making the basis orthonormal. So any questions about how that's done? Why all those different things need to be done? Anything else about this?
The fractions were you're multiplying each of those vectors by. You got those just by squaring our results of the Pythagorean theorem equations, right?
Yeah. So
Okay.
yeah, basically, the Pythagorean theorem, yeah, it works in as many dimensions as you want. So yeah, once you find those lengths, basically if you divide every component of those vectors by that length, then you normalize it. Rather than rewrite the vectors that way, I just multiplied the vector by all the scalar 1 over the length.
For
What
the
else? Oh, go ahead.
for the second one, the 3/2,
Yep.
is it the square root of 2 over 3, or is it the entire equation, the entire fraction, square root times the
It's the square root of the whole thing. Square root of 2 over the square root of 3. So I got 3 halves up here, right? That means that 3 halves is equal to the distance squared. So the distance is equal to radical 3 over 2. But then I want to divide every one of those components by radical 3 over 2. That's why I have the reciprocal here. The reciprocal is equivalent to 1 over this. All right. Anything else about this Gram-Schmidt process? Okay, let's go to a new page. All right. Who's next?
Could we do 3A?
From the same file?
Yeah, yes, sir.
All right. 3A is all right, so you're given a set of vectors. 1, 2, 0, 0. 0, 0, 3, 5. 4, -2. -5, 3. All right, and part A says to determine whether this set of vectors is orthogonal. So how do we determine if a set of vectors is orthogonal?
didn't we just do it in the last question?
Yeah. So the last question, we were trying to basically manipulate vectors to make the dot product equal to 0. Now we want to make sure that this given thing has those dot products. So 1, 2, 0, 0 dot 0, 0, 3, 5. I think that's going to be fine because all the the zeros, the non-zero entries don't really line up. So 1 times 0 plus 2 times 0 plus 0 times 3 plus 0 times 5. So that one's good. Not enough though. We need to look at all 3 pairs. So 1, 2, 0, 0 dot 4, -2, -5, 3. I'm going to go ahead and skip the ones that have zeros in them. So 1 times 4 plus 2 times -2. That's equal to 0. That's fine. And then finally 0, 0, 3, 5 times 4, -2, -5, 3. So 3 times -5 plus 5 times 3, also 0. So yes, the 3 vectors that we have, they are orthogonal set because all of the pairwise dot products are equal to 0. All
And
right, what's
then
next?
the
Oh, go ahead.
projection for B of that problem, we
Yeah.
do the what is it? The
So B, find the orthogonal projection of U. Basically U onto that subspace. 1 -2, 3, 5. So this right here, we just learned. This is the orthogonal basis of some subspace. I think the test called it W. Orthogonal basis of W. U is a vector that is probably not spanned by this basis, but we want to find the orthogonal projection of U. So let's do this. I'm going to draw the same picture again. Here's vector U. And then I'm going to let this single vector represent all of W. One of two things is possible. Either U is spanned by W, or U is in the span of W, or it's not, and there's some vector within W that's closest to U, that comes closest to being U. And I think there's a special stipulation on here. What does it say? Find the orthogonal projection of U onto W without inverting matrices or without solving any systems of linear equations. So, I mean, we do have a way to normalize some matrices and do that kind of calculation, but we don't have to do that in this case. And the reason we don't have to do that is because we have an orthogonal basis, and that allows us to do some different things. So we can kind of get by with this by using a dot product. Basically the same way we just did, but this orthogonal basis, basically what we're trying to do is this. I would like to find the linear combination of the vectors in this orthogonal basis that comes closest to U. And since this is an orthogonal basis, that means that the directions of these 3 vectors don't have anything to do with each other. They're completely independent, which means that if I find basically the number of vector 1 that I need and the number of, it's not going to affect anything in the direction of vector 2. So that allows us to do this. Basically, the way we find our orthogonal projection is by this dot product. I want to project U onto W. I can't do that all at once. I got to do it a vector at a time. So let me call these V1, V2, V3. So U dot V1 over what? What do I want this to be over? What direction do I want to be in? I want to be in the direction of V1. So in the past example, we like our denominator was all based on the U vectors. In this case, since I'm projecting onto W, I want to stay in the direction of V1. So this is the dot product I'm going to do. So what is u dot v1? 1 times 1 is 1. Negative 2 times 2 is -4. 3 times 0 is 0. 5 times 0 is 0. So 1 minus 4 over v1 dot v1. So 1 times 1 plus 2 times 2, that's 5. And then we'll multiply, whatever that ratio is, and we'll multiply that by v1. So v1 is 1200. So I get negative 3 over 5. Times 1200. So negative 3 over 5, negative 6 over 5, 0, 0. And now I'm just going to repeat this process with the other two vectors that make up the basis, not u1, just u, that make up the basis for w. So u dot v2 over v2, v2, v2 dot v2 times v2. That dot product is going to be 3 times 3 plus 5 times 5, so 34 over v2 dot v2, which is also going to be 34. So this one's a little simpler. So again, I'm looking for the linear combination of the vectors in v1, v2, and v3 that I want. The multiple of v2 that I want is simply going to be 1. So this is going to give me 0, 0, 3, 5. And then finally, u dot v3 over v3 dot v3 times v3.
So it's u times the vector we're comparing it to for each one.
Yeah, and since your basis is made up of many vectors, basically what we're trying to do is this. I know that, or I don't know. I'm assuming that u is going to share some directionality with every vector in the basis of v1, v2, and v3. So I'm trying to find, all right, what part of u is parallel to v1? We've done that. And then we have to do the same thing with v2 and v3. Whatever the sum of these three things that I come up with, this will be the vector in the span of w that comes closest to this given vector u.
Okay.
Because we have to repeat this for, I can't take a dot product with any more than two vectors at a time. So I can't deal with the basis all at once.
Okay. So
Go
in
ahead.
the one dealing with the second vector, there's just like a mark. It's not actually like a subscript for u.
Yeah, I got so used to writing u1 that I wrote a 1 there, but it's just, our vector is just u.
Okay.
The only thing we're changing is the different family members of v. All right, so u dot v3, so 1 times 4 plus negative 2 times negative 2 plus negative 5 times 3, so minus 15, plus 5 times 3, so plus 15, all over v3 dot v3, so 16 plus 4 plus 25 plus 9 times v3. So this is 8 over what? 20, 45, 54. 8 over 54 times 4, negative 2, negative 5, 3. So 4 times 4 is 16 over 27. Negative 8 over 27. negative 20 over 27, and 12 over 27. All right, so what did we just do? These three pieces right here, these are basically the components of vectors v1, v2, and v3 that are parallel to u. So to find the orthogonal projection of u onto the entire subspace, my final answer is going to be whatever I get when I add these things together. So negative 3/5 plus 16 over 27, negative 6/5 minus 8 over 27, and so on. So that'll be your final answer for the orthogonal projection.
On the document with the multiple practice exams, they had a question that was similar to this, like trying to find the orthogonal projection. It states that like the original matrix or three vectors that are given are not orthogonal. And it kind of had this method where you glue all the vectors together and call it A, call that like U vector B,
Yep.
transpose the main matrix, and then use that like A transpose A inverse, multiply
Right.
A transpose B and or B.
So that is a method for doing this, but in the question that I was the document I was looking at, it says I'll read it again. Find the orthogonal projection of U onto W equals span of V1, V2, V3 without inverting any matrices or solving any systems of linear equations. So basically we were forbidden from doing that. So that is a valid method, but basically we were dictated to use something different.
Okay. And I just one more question. While you're doing that final step there, are you adding all three of the matrices
Yeah.
together?
So yeah, negative 3/5 plus 0 plus 16 over 27, and so on.
Okay. All right. Thank you.
Yep, no problem. All right, what else?
Is question 4 something similar?
Let me see. Yeah, it is. But yeah, in question 4, you are not. You're just given two vectors. So question 4 is set up like this. So W equals the span of 1, 1, 3, and 1, negative 1, negative 1. And we want to find the vector in that span that's closest to this. But I don't think I can use the process that I just used. In fact, I cannot. So to recap, this process here, in like this method of using these different dot products to kind of pluck out, all right, what are the coordinates of V1? What's the coordinate of V2 and V3? This approach only works if the basis I have is orthogonal. Because basically what's happening is this. All right, let me go back to I'll give you a kind of a schematic diagram of what I'm doing here. Let's say that I want to get from here to here. And I'm telling you, all right, the only directions I'm allowed to move are this direction and this direction. I'm trying to make these perpendicular. If that's the problem, then it becomes very simple to do that, because the direction right has nothing to do with the direction up. So basically I can just break this into two pieces, figure out how far I need to go right, how far I need to go up, and we're good. That's if the two directions were orthogonal. What if instead I have this, the direction right and the direction of this? This becomes a much harder thing to answer, because moving to the right inherently has something in common with this other direction, and vice versa. So let's say I took one of these steps. Well, that just doing that reduced the number of this diagonal direction I would have to do, because they share some directionality. If they're orthogonal, you don't have to worry about that kind of interference. So that's the situation we're in now. And just to be clear, how do I know that these things are not orthogonal?
Because
How am
when
I
you
saying
add
that?
them, they don't add up to 0.
That's not when you add them.
Oh, right. Dot plot.
Yeah, the dot product is 0, or is not. So when you have vectors that are orthogonal, the dot product will be 0. In this case, you have 1 minus 1 minus 3. That tells me they're not orthogonal. So they share some directionality. But I can still answer this question. I just have to, there's another approach that I have to do. So what Quinn was talking about is I can basically stitch these vectors together. So basically put these two columns together to form this 3x2 matrix for this basis of something. So let's say this, U is just some generic vector. I'm going to say the vector P is the vector in W closest to U. So here's U, here's P. I would like to find what P is. So finding a vector in some subspace that's closest to some other vector, that's equivalent to asking for the orthogonal projection. So what we're looking for is this. I know that if I find some combination of the coordinates of A, or the coordinates of the vectors of A, so let's say this is V1, this is V2, and I multiply that by this column vector, C1. How many coordinates do I need? I just need 2. C1, C2. Then I will get P. But I want that P to be something really close to U. So let's call this other side K. I know that P dot K is going to equal 0. So I mean, so let me do this. I've derived this before in class. Let's kind of focus on, let's flash forward to the end here. What I want to do is figure out how to find P, and that comes from this, basically normalizing this equation. I can't really get rid of A because A, like the way to like get rid of a matrix is to multiply it by its inverse. But A is the wrong order to have an inverse. So that can't be done. So that's where we take this kind of, we manipulate to we want to multiply something by A to give us a product that will definitely have an inverse. So that's what we multiply on the left by the transpose. So now I can rewrite this equation like this. A transpose A times the coordinate vector. So this thing right here has an inverse. So P equals A transpose A times the inverse. Am I going too fast here?
What's C1 and C2 again? How do
C1 and C2, those are the basically the coordinates. So basically the part of what I want here, I'm looking for the linear combination of these two vectors, V1 and V2. So C1 and C2 are their coordinates. Basically, how many of V1 do I need? How many of V2 do I need? That's what C1 and C2 are defining here.
Okay.
Yeah, I said I wanted to flash forward to that normalization equation. Let me go find that, rather than trying to derive it off from scratch again, which will take a while. All right, so here's what we want. P times A transpose A inverse times A transpose B. All right, so what are all these pieces? A is the matrix that's made up of these basis vectors stitched together. So we've written down A, but what's B? B is the thing that I've been calling U. That's the vector that I want to try to minimize my distance to. So in this case, B will be 308. So you should be able to enter matrix A into your calculator, do all these other different manipulations to it, and get a vector P that is reasonably close to B. So basically, the last two questions we looked at are two different ways of answering the same question. So basically, if you're given vectors that define, or you're given vectors that span some subspace, and you're given some other arbitrary vector, I would like to find the member of this subspace that's closest to the given vector. So just to recap, why do I need these two different methods? Well, in the previous example, we had an orthogonal basis, which kind of opens the doors up to this dot product approach. The question we were asked, the one from the test, it specifically, prohibited us from using this approach we just did here, but it would absolutely work. This approach we just did on this page, this works for any basis. Doesn't have to be orthogonal, doesn't have to be normalized. but just to be clear, we could have done this. We could have done P equals. So let A equal this 1, 2, 0, 0, 0, 0, 3, 5, 4, -2, -5, 3, and B equals 1, -2, 3, 5. We could have done the, I already forgot again, was it A transpose A inverse? A times A transpose A inverse. So this right here would have given us the same result.
So in these questions, what kind of vocabulary are we looking for specifically to know which one is which? Or
I mean,
I'm
so
just,
they're both asking for the same. So let me read the questions three. So 3B and 4. So 3B says this: find the orthogonal projection of U onto W. So basically, or find the orthogonal projection of some vector onto some subspace. And we were given the condition or the stipulation without inverting any matrices or solving any systems of equations.
mm,
4 says this: let W be some subspace, and they're given the basis. Find the vector in W closest to the vector U. So different words, but really those are both asking for the same object. I have a subspace W. I have some other vector U, which, is implied not to be in this span. But even if it's not, there's some vector in W that comes really close, or that comes closer to U than anything else in W, and I can still find that. So even though I use different words, that's the object that we're looking for. So one question used this term, orthogonal projection of U onto W. The other question used this term, the vector in W closest to U. So very different words there, talking about the exact same thing. So the orthogonal projection, what is the orthogonal projection of a vector? It's like, all right, W is the thing I'm trying to project onto. This vector U, it resembles everything in W to varying degrees. I want the one that it resembles the most. So the one who's like, we talk about, so I've said a few times tonight, like, whose directions, like what directions are the most similar. Another way to think about that is, even though we're not calculating it, you're kind of looking at the angle between these two vectors. I'm trying to make that angle as small as possible. That's what the orthogonal projection does.
all right, thank you.
Mm-hmm. All right, what else?
The next question is finding the orthogonal complement to W.
Okay. So question 5. All right, so it says let W be the span of two vectors. Find a basis for the orthogonal complement to W. Okay, so V1 equals 1, -1, 2, 4. And V2 is equal to 1, 4, -9, -8. So W is equal to the span of V1, V2. And I want to find the orthogonal complement of W. So what is that?
It's the vertical, the what is it, perpendicular line to W?
Yeah, so basically, W is a subspace. It's the linear combination, all the linear combinations of V1 and V2. Some things are going to belong to that, some things are not. What I want to find are the things that don't even come, like I'm speaking very informally. I want to find the things that don't even come close to that span. I want to find the things that share no directionality with V1 and V2. So basically, I want to find vectors that look like this. V1 dot U equals 0. V2 dot U equals 0. I want to find all the vectors U that look like that. So knowing that that's the thing I'm trying to make, so let's talk about this. What does it mean to dot V1 with U? I don't know. I have no idea what U is, so let's just say U is equal to this. X1, X2, X3, X4. And I know that when I dot V1 with U, I get 0. So another way of saying that is this. If I dot those together, I get 1 times X1 minus 1 times X2 plus 2 times X3 plus 4 times X4 equals 0. And then I could set up a similar dot product for V2. But basically what's going on here is this. If I put these vectors together in a matrix, basically what I'm looking for is their null space. Because when I dot each one of these with, oh, I made a serious mistake here. I can dot these together because they're the right order, but I cannot do this. I can't do X1, X2 because the dimensions are off. So what I have to do is transpose this. So if I transpose it, what do I get? I get 1, -1, 2, 4, 1, 4, -9, -8 times X1, X2, X3, X4. Now this thing makes sense. And when I multiply those things together, what I want is this. Keep making things the wrong size. The guy gets 0, 0. So basically what I want the null space of this 2x4 matrix. Basically, I want to know what combinations of X1, X2, X3, and X4 are going to give me the 0 vector. So what I would like to do is this. I would like to reduce row echelon form this matrix. 1, -1, 2, 4, 1, 4, -9, -8. because this will tell me what the null space is. Which I can try to do it before one of you does, but if you get there, go ahead. All right, here's what I got. One, oh, go away. 1, 0, negative 1/5, 5/3, 0, 1, negative 2 1/5, so negative 11/5. Not 5/3. 8/5. And then negative 2.4 is negative 12/5. Okay, so that's what I get for the reduced matrix. So from here, how do I get the null space out of that? So let's reinterpret these two rows. So I get x1 equals 1/5 of x3 minus 8/5 of x4. And then I get x2 equals 11/5 of x3 plus 12/5 of x4. So that is enough for me to build the basis for a null space. Which when I have that, that's the orthogonal complement. So I have two parameters, x3 and x4. What I'm building is this, x1, x2, x3, x4. And I'm parameterizing it against x3 and x4. All right, so x1 equals 1/5 of x3 minus 8/5 of x4. x2 is equal to 11/5 of x3 plus 12/5 x4, and x3 is equal to itself, and x4 is equal to itself. So basically these two vectors right here are the orthogonal complement, because any linear combination of those two things are guaranteed to be perpendicular to both this v1 and v2. Okay, any questions there? I haven't heard from any of you in a while. All right. So what was that? That was question 5, I think. Yep. All right, what else?
Could we perhaps go over question 7, the linear transformation?
Yeah. All right, so number 7. All right, so I'm told I have a linear transformation from R2 to R4. Defined by, and I'm given 2 examples. L of 2, -1 equals 1, 1, -3, 4. And L of -1, 0 is equal to -5, 6, -3, 7. So what I want to find is this. I want to find, so I know L is linear. So L of X is equal to A times X. I want to find this vector A, or this matrix A. So something that's always basically a given is that if you have a transformation that is linear, then you must be able to represent it as a matrix. So I want to find that matrix A. So how do we do that? So we should probably figure out what the order of A should even be. So I know that this happens when I multiply A times X, which is a 2-dimensional thing. I get an output vector that's a 4-dimensional thing. So what does that imply about the number of rows and columns in A?
Four by two.
Should be 4 by 2 because this is a 2 by 1. This is a 4 by 1. The only way for this to make sense is if A is a 4 by 2. Okay, so A is a 4 by 2 matrix. So how can we figure out what it looks like? So one thing we've talked about, or last time I saw you in class, we talked about this idea of what basis are we going from and what basis are we going toward. In this case, we're going from R2, but it's with respect to something non-standard. So I'll call the basis B, but what does the basis B look like? Well, we're going from R2, so it better be a 2 by 2 matrix. So the columns in this basis are going to be negative 2, -1, -1, 0. So basically, what's happening when we defined basically, or did we guys didn't define it? We have 2 examples of how L works. So basically, what we're going to do with those 2 like input examples or 2 examples of input vectors is we're just going to say that's the basis on which this transformation operates. So my basis B is this. Another way to look at it is this is what this is the matrix I get from stitching together these 2 inputs. So what do I do with B? So here's what I know. I know when I multiply A by B, I get what? Let me write B as is. A times 2, -1, -1, 0. Well, I was given what happens column by column, which means that the matrix that comes out of this is those columns stitched together. All right, so where do I go from here? How do I work towards figuring out what A is?
You reduce in row echelon and then parameterize.
What am I reducing?
The 4x2.
But I don't know what the okay, sorry. I was thinking of A. If we reduce the matrix on the right hand side of the equal sign, if we reduce that, what's that going to give us?
Not what we need.
I don't think so. So what we're gonna basically work with here is it's gonna look similar to what we did with basically trying to find an orthogonal projection by normalizing a matrix. So here's what we know that A does. A is if we think about it in the columns that stitch together, it's basically this. A is equal to L of 2, -1. And L of -1, 0. So let's go back to this equation here. I want to solve for A. Or in other words, I want to isolate A. How can I isolate A? How can I get A by itself? Give names to this. This is I call B. I'll call this C. So basically what I have here is this. I have A times B equals C.
We could take to get A by itself, correct?
Yep.
We could try taking the inverse of B on both sides.
Yep. So now, does it make sense to think about the inverse of B? Does B have an inverse? Because if it does, we could do this. A times B inverse equals C times B inverse. So a couple questions here. What kind of matrices have inverses? So the only kind of matrices that even have inverses are square. So this one's square. And matrices are invertible if their determinants are not 0. So we can find the determinant of this 2 by 2 matrix. 2 times 0 is 0, minus 1. So the determinant is equal to -1. That means we have an inverse, which means we can talk about B inverse. So that means A is equal to CB inverse. So yeah, put C into your calculator, put B and C in your calculator, do this operation, and you will get what A is. All right, I have almost 9 o'clock. Any last minute things before I go?
Just to make sure, you did say that units 6 and 7 are it's supposed the final is supposed to be made up of mostly units 6 and 7, correct?
Yeah, yeah, more emphasis on those.
Okay, thank you.
Is that not what we did just now? Are these, is this
No,
practice
that's like
final?
I
Not
think
really.
I think except for the very first question you asked, which was question number 1 from this file, I think everything else has been from 6 and 7. I'm just going back through to make sure. But orthogonality, chapter 6 is all about all the many things to do with orthogonality, and chapter 7 was all linear transformations. So tonight, I think we mostly talked about chapter 6. This last thing we did was from chapter 7. You're welcome. All right. Yeah, I think I'm gonna go ahead and sign off. It's 9 o'clock. If you have any last minute questions, go ahead and email me, but I'll post this video as soon as it's done processing.
Can I ask one quick question, sir?
Go for it.
I don't know if you're familiar with the first document you posted with the 3 practice exams. I've really put a lot of hours into studying those 3 specific practice exams.
Yeah.
I believe it does cover a lot of chapter 6 and 7, especially with orthogonality or orthogonality. I'm just curious, I'm just kind of nervous about the span of content that's going to be on the final exam. Do you think if like you mastered these 4 exams you posted, this one we just went over, and those 3, do you think you'd be pretty well prepared for the content of the final?
Yeah, I mean, so like run down the like the really big ideas from chapter 6 and 7. So chapter 6, what does orthogonality mean? Can you determine if you have orthogonality? If you don't have orthogonality, can you force it? That's what the Gram-Schmidt method is. If I give you any basis, can you make it orthogonal? Can you use orthogonality to find projections or closest vectors? Those are the same, same ideas repackaged in a different way. What else we do with orthogonality? I think that was about it. So like there are a lot of different ways I could kind of ask you those things. Or finding the orthogonal complement was something we did. We did that tonight too. Oh yeah, something we didn't talk about tonight was this idea of, least squares solutions, or lines of best fit, curves of best fit, kind of those kinds of things. Those are very much the way we find those like best case solutions. Those are very closely related to orthogonal projections. So knowing how to adapt those, adapt the things you do with orthogonal bases to find those best case solutions. Chapter 7, there were 2 sections there. The first one is all about, what is a linear transformation? If you have one, can you represent it with a matrix? And we did had a few different looks at that. We didn't have time to talk about question 8 on the final. We spent most of the night talking about, but question 8's a good one to look at. And the second part of chapter 7 we looked at was basically properties. So what is the kernel of a transformation? What is the image? What's the rank? Can you tell if a transformation is 1-to-1 or onto? So keep an eye on, yeah, maybe refresh what those terms mean and how to find those things. But those are the real big ideas. I mean, so the final will mostly emphasize chapter 6 and chapter 7. You might see some of the more fundamental things from previous chapters. But yeah, I think to answer a long way around to answer your question, I think if you feel good about the finals I posted, like the sample ones and anything that you've found on the website, I would feel like you're in good shape.
Thank you. Appreciate it.
Yeah, of course.
Thank you. Have a good
Yeah,
night.
no problem. Have a good night.
Thank you.
Thank you.
Thank you.